Hi, in the today's session, we'll be actually doing the Friedman-Nemnine test for statistical significance to compare different algorithms on multiple data sets, right? So we're actually doing this sort of say quick tutorial on this particular one because a lot of people were actually asking this question to me. So I actually prepared a notebook and a quick run for this one. So let's actually before without wasting time, let's actually go to our notebook. So firstly, you will actually need to install this. Firstly, you will actually need to install this particular package, that is a scikit post hocs, right? Scikit hyphen post hocs. That's you actually need to install. So how would you actually install into Colab is actually by using this exclamation operator. You can also type the percentage symbol, or nowadays you can also directly do pip install and the particular package name. As this package is already installed in my Colab environment, so it will show me the requirement satisfied, but for you it will actually just go ahead and install the particular package which you will be needing. So firstly, before going towards anything, you will actually you must have the datasets which you want to actually process on. For example, my dataset is such something like this, that this particular data actually refers to three particular algorithms which are run on four different data sets. So they are one algorithm, second algorithm, and the third algorithm. And these are four as the data set, that is data set 1, data set 2, data set 3, and data set 4. So what I am wanting to do is that I want to find that whether the three algorithms are actually similar or not. That's what the main purpose of Friedman test, right? And if there is a significant difference between two such algorithms among these, right, or any, or even three are can be different, right? So then we can actually perform Nemeni test, right? What it will tell me is that among these algorithms, which pairs are actually similar, but which pairs are actually different, statistically different, right? Because values will be different, right? You will actually always get the values which are different, but how much different, right? That's actually you will get by statistical significance, and you can actually easily use this in your research paper to actually prove your statistical significance over the results, not just actually providing the metrics. Okay, so you will actually need these libraries for your run. Firstly is actually NumPy. You will actually import NumPy as NP, and then you have the pandas as PD, then you have the scipy.stats as from the scipy.stats you will actually import this particular function, that is Friedman chi-square. That's actually a method which will actually do the Friedman test for you. And then you have to import the scikit post as SP, right? You don't need to install SciPy in the Colab environment as it's already installed. So that's actually about the libraries which are actually being used. Now, you have already prepared your data set in the NumPy array, and by this command, right, you will actually get your data set in the list, and then we'll convert it to the NumPy array by passing it into np.array function. After that, you will also store your algorithms in a list named algorithms, right? And with all the algorithm names, whatever you wanna suggest. For example, if I am actually training a classifier, then I will have naive Bayes classifier, decision tree, and the next classifier in this list, right? So now I was actually wanting to show you that what this data.t actually will do. As you know that you have a NumPy array, so you can do all the operations like what you can do with the NumPy array. So you will actually do data.t to actually transpose all this, right? So why did we did this? Is it because while passing the things to the Friedman chi-square function, you will need to pass one by one for each of the algorithms. So what this command is actually doing is that it is getting me the things into the row wise for each algorithm, algorithm 1, algorithm 2, and algorithm 3. And then I'm actually passing each of the algorithm as a separate argument here by using this star operator, right? Essentially, you might have also done is actually you might have passed data 0 part, data 1 part, and data 2 part in such a fashion to this particular function, right? This function will do all the calculations automatically behind the scenes, and then it will actually give you two particular things. One is actually Friedman statistic, and another is the p-value, on the basis of which you will judge whether there is a statistical difference between all the algorithms or not, right? So you are getting two things, right? So we are just printing it with this formatted string that is statistical significance is 6.5, and then you have the p-value to be 0.03. That's what we got. Now we have to rank the different things up, right? We have to rank different things up, right? That's actually a critical step in the Friedman-Nemnai test, is that you need to rank. For example, we have these sort of say data, right? So you will rank multiple algorithms such that for each of the data set, what is the rank of this algorithm, what is the rank or say order of that algorithm. So highest performing algorithm in our case is this one, right? The second algorithm. So the rank of this algorithm will be 1. And then we have the 80 to be the second algorithm, so the rank of it will be 2. And for 0.78 we have the rank to be 3, so that is 1, 2 and 3. In this fashion the rank is actually calculated. Similarly you will do for all the data sets, right? Behind the scenes it will do for all the data set, and then we have to average for each of the algorithm so that we can get a rank of each algorithm. Lesser the rank value, that is 1 is being the highest, means the most outperforming algorithm, right? So, and after that, we can actually get the difference between the ranks of two algorithms and compare it with the critical difference, and then get whether both the algorithms are actually similar or different, right? So, we have what we have done is we have calculated the rank through this command. What it is doing is that it is doing nothing, but we know, okay, we have to rank the most valued or most accuracy algorithm to be the lowest, that is actually 1. So what we are doing is that we are doing the negate of the data set, as it's an NP array, so it will be actually negating it. And then we are doing the arc sort, and x is equal to 1, so that is actually sort all the ranks row wise, right? For each of the row it will actually sort the things out. And then plus 1 is because arc sort will actually give me from values from 0, so plus 1 will actually add me the things from 1. So what it will do is that it will do the things row wise and for all the data set, right? So this will actually calculate me the rank for all those. For example, for the first row we have calculated 1, 2, 3. So that's actually the same thing which we have got here, that is 1 and 2 and 3 in this fashion, right? And then we also need to do the average ranks, that is we need to do the 2 plus 2 plus 1 plus 2 and divide by 4. That's what we need to do. So we are doing this with this command, that is np.mean, and then x is equal to 0. That is you have to actually take up the x 0 along which you are actually taking up the average, right? So we have done that, and we have got three particular say average ranks for this thing, right? So okay, so we have got the average ranks and we can actually print it out, right? That is this algorithm is actually having this much of rank, and this algorithm is actually having this much of rank. So seems like the algorithm 3 is actually outperforming all of the algorithms, right? Now as we have seen, the p-value was coming out to be say what it was coming out to be. It was coming out to be 0.3, I believe. Yeah, it was coming out to be 0.03, right? So our particular threshold which we have kept is 0.05, right? So we need to also check that whether the particular p-value is less than this. Yes, this is less than that, then it means that all the algorithms, there is some at least one algorithm which is statistically different from all of those algorithms. So that's what it means and how you need to interpret it, right? So yes, we will actually just print, okay, so significant differences are found. Then what we will do is that we will actually prepare our data for the NIM9 test. Till yet Friedman test is done, you got the ranks, you got the average, you got the statistical metric. Now we are doing for the NIM9 Friedman test, right? So basically what we are doing is that we are getting the same data, just the columns are being named with the algorithm names, algorithm 1, 2 and 3, and we are just making a data frame. That's it. And then we are passing all the values, means all the values, number array values from this data frame to the POSOK Neyman Friedman NIM9 Friedman test, right? In this fashion you need to pass the data set. Firstly you just convert it to the data frame and then pass to the POSOK Neyman Friedman test, right? By calling the sp dot, because sp was the ls which you actually get for the scikit-learn process, right? After that you will actually just use the df.columns. What was df.columns? Df.columns will actually capture the name of the algorithm, so you will actually use them as the index and also as the columns, right? Because it will actually give you a matrix, right? Means this algorithm are this much different, something like that. So you will actually get the pairwise value for all of the algorithms, right? So when you will actually print it, so you will actually get something like this, right? That whether algorithm 1 and algorithm 1 are actually similar. Yes, is they are totally similar. So 1 is the score, right? And algorithm 1 and algorithm 2, 0.75 is the score. Similarly, for all the diagonals, we will actually get a score of 1, right? Because they are totally same, right? And for algorithm 2, algorithm 2, same, algorithm 2, algorithm 3. So in this fashion, you'll actually get the score, right? Now we will see. Okay, so now we need to see which two particular algorithms are same and which two are different. So what we are doing is that we are keeping a significance level. Okay, so we have kept the significance level to be 0.05, and if the value is coming out to be, say, even less than this 0.05, means means it is very very less value, then it means that they are totally different, right? It means they are totally different. There is no similarity between those algorithms, and if it's actually greater than that, then the algorithms are same, similar. So we will actually keep the significance level into a particular variable, and we will traverse through two for loops, right? Like we used to do in selection sort. We are traversing the first for loop for the algorithms, right? And then the next for loop for the algorithm which is numbered one after the previous one, which is actually indexed by I, right? So we'll actually do the range from I plus 1 to len of the algorithms, right? And then we are actually getting both the algorithms, and then we are getting the value for those two algorithms by using the ilog, right? You might remember that we can do the ilog in this particular case, right? Because whatever it returns, we can do the ilog, and we can get the I and the j position by passing in such a fashion that I comma j, right? Because in the data frame we can actually get through this fashion a particular value. So we can see if the values if the particular value of these two algorithms is less than significance level, we can print that yes, they are both different, otherwise they are same. And even if the p-value earlier calculated by the Friedman test was actually greater than 0.05, then it means that there is no significant difference, and then we can just skip this particular NEM9 test. So this was all about the Friedman NEM9 test, and yeah, this is what I can actually bring in a quick tutorial. If you want, I can also bring more tutorial about how to plot the critical difference, and how to have such a beautiful plots about the critical difference for these algorithms. And yeah, thank you so much for watching. Let me know what you need to see in the upcoming videos about the research, about the machine learning, and about deep learning. I'm actually available for all of those, and I'm also making videos about software development and app development and much more. So just let me know what is the content actually required, and I can actually come up with nice tutorials on this. And thank you so much, guys.